So purpose of this talk is to describe a very small subset of the measurements that people are trying to make all over the world to try and discover physics beyond the standard model through weak decay processes. And you've heard a lot about neutrinos already, so although I will mention some things due to neutrinos, I'll concentrate mainly on quarks. Now, you've probably all seen this many times. This is the standard model with the Higgs added. And one of the problems that we're trying to address is why are there three generations of these quarks, and why are the interactions different among them? Okay. And that's true both in the neutrino and the quark sector. Now, quarks generally are mixed with each other, which can be described by the fact that they decay in this very strange pattern. Some of this is just due to mass effects, like the top line quarks are heavier than the ones on the bottom line. These are the charge 2/3, these are the charge minus 1/3 quarks. And this mixing between the base states of the quarks, which allows these decays, these transitions to occur, is described by the CKM matrix for quarks here, which is shown here. And it is described by 4 parameters because it's a unitary 3×3 matrix, 2 of which are well measured, lambda and A, and this provides constraints on the parameters rho and eta. These are fundamental constants of nature in the standard model, and they have to be measured. They're as fundamental as G Fermi or alpha E&M. Okay. Now, since this talk's addressing physics beyond the standard model, just a quick reminder that we have dark matter that we believe through various sources. We have dark energy. We have a hierarchy problem, which is basically divergent quantum corrections that go from the electroweak scale of 100 GeV to the Planck scale without fine-tuning the quantum corrections. Actually, all of these above issues may only be related to gravity. So there are other issues which are really important for our field and understanding nature, and that is the flavor problem. Why are there 3 replications of quarks and leptons? Baryogenesis, which is related to the fact that we're actually here. The amount of CP violation observed thus far in the quark sector is too small. We observe a baryon-antibaryon difference divided by actually the average photon entropy, but I just called it N gamma to be short. We observe something in the quark sector of about 10 to the minus 20, but we need something about 9 orders of magnitude larger. So missing by 9 orders of magnitude is not a good thing. So new physics must exist to generate the needed CP violation. There may be some left in the quark sector that we haven't seen. It may be in the neutrino sector or the Higgs sector. To explain the values of the CKM couplings, this is another reason why we need new physics. We don't understand this, both for the neutrino and quarks, and to explain the masses of fundamental objects. Are they related to the CKM angles or not? We don't know. So, for example, here's a picture of the CKM matrix for quarks and the PMNS matrix for neutrinos. Just diagrammatically, the sides of these are related to, equal to the CKM element. So the area is the matrix element squared, which is what comes into the decay rate. And you can see that the quark CKM matrix is very strange. There are very, very small elements in the corners. The off-diagonal elements have some symmetry, but they're of different size, and the diagonal elements are actually very close to 1. Very different than the neutrino matrix. Are they related? Is there some physics that tells us why these things should be this way? Are they related to the masses of the fermions? We don't know. Here are the masses of the fermions, and the remarkable thing about this picture is it goes over 12 orders of magnitude, and the heaviest fundamental object in the standard model, the top quark, is as heavy as a tungsten nucleus, yet we consider it to be a point particle. So these are the problems. Now, we're looking for new physics, and I want to point out that flavor physics is really a tool for new physics discovery. Okay, while measurements of the fundamental constants are actually fun, the main purpose now is to find or define properties of physics beyond the standard model. Now, we do this because flavor physics probes large mass scales via virtual quantum loops. And a simple example of the importance of such loops is the Lamb shift in atomic hydrogen, which is given by photons and electrons here. And the small difference in energy between the two S1/2 and two P1/2 energies, you should remember this from your quantum mechanics class, these should be of equal energy of lowest order, and they're not because of these virtual loops. So that's the idea. We're going to look for particles in loops. In fact, another example, which is much more recent and at much higher energy, is the mass of the W changed due to the T quark. So you'd have an internal loop like this, which changes the mass of the W. And once you knew the T quark, there was another loop of a higher order, where the Higgs mass generated some change to the W mass. And this actually gave predictions of the Higgs mass prior to discovery. So loops are important. Now, it's often said that we have not seen new physics, yet what we observe is the sum of standard model plus new physics. So how do we set limits on the new physics then if what we see is actually the sum of both? Okay. Well, you can make some hypotheses. One oft-used hypothesis to assume that tree-level diagrams are dominated by the standard model and loop-level diagrams could contain new physics. So here's an example of a tree-level diagram. This is basically a beta decay of a B quark. Okay. It happens with one gauge boson. And here's a loop-level process which has two gauge bosons in it, which is B sub S mixing. And this is a diagram in the standard model. Here you actually have a B quark and an S bar quark, which is an anti-B sub S, which transforms into a B sub S meson through this diagram. So this is an example of mixing. And here's an example of a diagram, okay, with supersymmetric particles in the loops. And it could be anything new in the loop that we don't understand. And these are two interfering amplitudes. So you get an effect where the interference of these two amplitudes, you may be able to see it, especially if you know what to expect in the standard model. Okay. So the idea here is to compare what you know from tree diagrams to loop diagrams. And this is done in a plot here which is much too complicated to explain in even 20 minutes. So I'll just tell you that this is the CKM parameter eta. This is the CKM parameter rho. And here are all possible measurements from tree and loop diagrams. And you can see this tiny circle here. It defines eta and rho. But more importantly, it says that all the measurements we've made here involving mixing and CP violation and beta decay of B quarks, even suppressed decays of B quarks, they're all consistent. Okay. So we can use this to characterize new physics, where new physics may be and what the size of new physics that's left is from these current measurements. And that's done by writing the amplitude, and we called M12 here. It's just the standard model amplitude times 1 plus a new physics amplitude magnitude and a new physics amplitude phase characterized by sigma. And the result of that analysis is that you can write the phase here versus the amplitude, and you can do this for B0 decays, and what you see is that new physics amplitude is limited to be about 20% of the standard model amplitude, which is not such a great limit. And the same is true in B sub S decays, where the limit's about 20%, almost independent of the phase in both cases. So that means there's a lot of room to explore for new physics amplitudes, and we should be getting on it, which we are. So the point is to get better limits. Actually, the point is to find new physics. Now, we already have some strong constraints of new physics if you compare individual measurements in cases where you have very good standard model predictions. So whereas before the other case was a generic discussion, here I'm giving you a non-generic discussion where you have a specific decay mode and you have specific measurements. So this process would be what we call inclusive beta S gamma. That is, you have a B quark that turns into an S quark radiating a photon. And that diagram is described here. Okay, you can either have a W and a pair of top quarks or a two pair of Ws and a top quark. And you can calculate this rather accurately. This was a calculation from Misiak. So you can see that this is sort of a 7% calculation. And the ratio that's measured is about at the 10% level or 8% level. So the theory and the experimental errors are about the same. And you can now take a specific new physics model. For example, this is, I'll give you the results in the two Higgs doublet model, but it doesn't have to be this particular model. It could be any model, but just as an example. So here's the measurement here, and here's the standard model theory, and here's the new physics theory with its uncertainties. So if you see where the new physics model intersects the measurement, you find it's here, and that gives you a limit of about 300 GeV for charged Higgs in this particular model, okay, with this particular tan beta value, which is low. This is a characteristic of the model. So you can do this for different models, and you get different excluded regions in model space. Now, another way of doing this is to take, for a different set of measurements, is we pick out many models and work out their consequences. So this was done in 2010. So here are many, many models that predict the branching ratio for BD to mu plus mu minus in this direction, and the branching ratio for BS to mu plus mu minus in this direction. And I'll show you on the next transparency why this is an interesting process. So here's the standard model point, and here's many, many models. A lot of these are supersymmetric. This is fourth generation, etc. So in this process, the standard model branching ratio is also accurately predicted. And this is an exclusive decay rather than an inclusive decay that I showed you before. But new physics can make large contributions. Why? Well, here's the standard model processes, diagrams for it. You see they're both loop diagrams. There's a W here and a Z, and there are two W's here. So this is loop diagrams. And this is the MSSM, which is a supersymmetric model. And you can put supersymmetric particles here, or anything else that your heart desires. And again, these would interfere. Okay, so you can get large effects here. Especially since, if you go back to here, you remember that the predicted standard model branching ratio here is, this is 10 to the 9th times. So it's on the order of 10 to the minus 10, and it's on the order of 10 to the minus 9 for B sub S to mu nu. So these are very small branching ratios in my neck of the woods. Okay. Now, actually, this mode's been seen, and it was first seen by LHCb at CERN, and also then seen very quickly thereafter by CMS. And here is the evidence. You can see there, you know, with small branching ratios, there's the signals are very small, but the backgrounds are shown here, and they're very, very small indeed. B sub D, there's no claim of a signal. There may be some events there, and this is the CMS data, and again, you see a signal at the B sub S, small backgrounds, and maybe something at the B sub D appearing. So here are the measurements. They're both around 4 standard deviations, and when you average them, you get above 5 standard deviations. And here are the average measurements. Now, if you put this on the plot that I showed you in 2010, so 2014, what's left is everything in this rectangle here. So many, many of these models have now been killed off. And the phase space for these models has been drastically reduced. And of course, future is to get these measurements to get even smaller and smaller uncertainties to see whether you're in agreement in the end with the standard model or not. Now, another way of looking for new physics is to use neutral meson mixing. Now, neutral mesons can transform, as I showed you, into their own antiparticles via this loop, second-order loop diagram. So here, P means any neutral meson. And the short distance transition rate depends on the mass of the intermediate quark in the loop. The heavier, the larger this amplitude is. So this favors mesons containing S and B quarks since the T quark is allowed in the loop. And it depends on the CKM elements from the CKM matrix I showed you before in these 4 corners. Okay. So here's just an artist sketch of what you expect. For D zeros, the red line is the mixed amplitude. So you don't, well, it's actually the decay rate. So you don't expect much in D zeros in the standard model. You expect something in B sub D, which has been seen, and you expect something in B sub S, but here B sub S, you notice, has these huge wiggles because the CKM elements here are all favorable, whereas here they're not so favorable. So there's been a lot of data. B-mixing has been known for a long time. It was seen at Argus first, in fact. Here is the LHCb measurements for B0 to D minus pi plus. And what we're looking here is at the oscillation frequency, which is characterized as a mass difference. Okay. in units of inverse picoseconds, because this is a time plot. This is the asymmetry of B0 versus B0 bar as a function of time. And you get a very accurate measurement here of about half an inverse picosecond. And for B sub s, you can see it's much larger. It's about 18 inverse picoseconds. And you can actually see the oscillations. These are the signals used to make the measurements. And you can see the signals are very clean, very little background. Okay. Now, the CP violation measurement is to use the mixing and to make a measurement of the time-dependent differential decay rate between an anti-meson going to a specific final state and a meson going to exactly the same final state. So you have to find the right final state where both the anti-meson and the meson can go to it, and that's the asymmetry you want to measure. And this, what you want to measure here is the size of this asymmetry. And the angle, the CKM angle on this, well, how the measurement appears on this plot depends on what the mesons are and the CKM angles and stuff like that. You have to translate it. Now, for B0 to J psi k short, a very famous mode, you measure the angle beta, which is this line here, and that's not predicted in the standard model. There's no way to predict what the size of this CP violation is. Now, that's been measured, of course, and that's why we get this little allowed space for eta and rho. For B sub s to J psi f naught, which is the CP eigenstate, and J psi phi, which is the self-conjugate mode, we measure an angle called phi s, which doesn't even appear on this plot, and it's predicted from these measurements. And in the standard model, this prediction is very robust, very small error. This should be 0.01. The number predicted here is minus 0.036 with an error of about 0.002. Forget that. Okay. The CP violation in J psi x goes through the interference of a process where the B goes to an amplitude A and decays into F, whereas the B sub s then mixes to a B sub s bar and then decays through an amplitude A bar. So you have two amplitudes. This is all standard model. There's a third non-standard model amplitude that would change this, and that's actually what we're looking for. So here's the decay diagram for B sub s, and it can go to J psi, and the SS bar can appear as a pi state or a KK state. If it appears as a KK state, the largest contribution is phi. If it appears as a pi, the largest is F naught. Okay, and again, this is how you calculate it more precisely in the standard model, but it's about minus 0.04 rads. Okay, so this is a good place for new physics to appear. B sub s to J psi phi is not a CP eigenstate. It's a vector-vector state. So you have to do an angular analysis to separate the CP odd and CP even components, but you can do it. So I won't go into details on that because that alone takes a half an hour to describe. Here is the mass spectrum of pi plus pi minus in J psi pi plus pi minus, and you can see a very, very strong F naught component here, which this final state was predicted before it was observed. And it turns out all of these are useful, that the CP odd content of this final state is more than 97.7% from all of the substructure here. And here it is on a log plot, and here's all the resonant substructure that's been untangled. And if you measure the CP violation in this mode, you get something like consistent with 0, but with an error that's much bigger than the standard model prediction of 0.173. That will be augmented fairly shortly by a measurement with 3 times the data. If you do J psi phi, there are several experiments that have done this, and mostly it's dominated by the LHCb result. So here's a plot of phi s, and you can see it's consistent with the standard model. Here's the standard model prediction on this plot here. And it's plotted at phi s, another parameter, delta gamma s, which is not involved to first order in a new physics search, but usually the data is plotted this way to make it clear what people are measuring. And the combined result is very close to the standard model value with an error that's still too large and needs to come down in order to see if we can see something new. So This is the LHCb result, which is the most accurate, and it has an error of 0.07. Remember, the standard model value was 0.04. So there's a ways to go here. Let me turn now to D0 bar mixing. This is a very interesting decay mode. You have a D star plus. This wandered off of the D0. So this D star plus goes to a pi plus D0 bar. Maybe it's trying to mix itself. I don't know. This provides an initial flavor tag. And then you look at the D0 decay. So a wrong sign D0 can appear via mixing or rare decay that gives the final state. Okay. Now that's called, one of the ways this can do this is through, not through mixing, but the D0 transforms into a D0 bar via a two-step weakened decay process called a double Lee-Cabibbo suppressed decay. And that just follows an exponential decay time. If it mixes, however, it depends on time in a more complicated way, and you can find the ratio RD, which is the ratio of doubly Cabibbo suppressed to Cabibbo favored decays, where you include the doubly Cabibbo suppressed decays and the mixed decays together. And then if you do this, you can write the decay time as this RD, and then this would just be, this is the ratio to the exponential decay. So you get an extra term here, which is quadratic in time due to the mixing. So if you do that, first you can look at the right sign signal. This is the right sign signal where the D goes to K minus pi plus, tagged with a pi plus, and this is the wrong sign signal where the D bar goes to K plus K minus. So this means it mixed, and you can see the wrong, or doubly Cabibbo suppressed decay. So you can see the wrong sign decays here. And if you plot this, this is recent LHCb data, you see, you can see clearly the quadratic dependence on time. From now, you say this is huge, but this is scale is times 10 to the minus 3. So this took a long time to see. It was actually first seen by a combination of B-factory and fixed target experiments, but you only saw an effect if you combined all the data from those experiments. This is in one experiment, and you get a measure of y prime versus x prime. So having seen this mixing in these, you say, let me look for CP violation, because the standard model predicts 0. Okay. And, I mean, or something at the level of 10 to the minus 3. So this is really a good place to look for new physics. And here's the measurement looking at the amplitude and phase of the CP violation in this channel. And nothing is seen yet, but you can see that the errors have to got shrunk down by a lot, which is, I guess, the theme of this talk. Now, let me talk to something a little more general. We've already excluded a lot of physics from these box diagrams, even though the amplitude is only 20% of the standard model amplitude. That still excludes a lot of physics. So you can write the effective Lagrangian as the standard model Lagrangian plus some operator divided by some mass scale squared. And if you take the coefficients to be about the same size as the standard model coefficients, you exclude regions from different mixing and CP violating decays in kaon, B0, BS, and DD bar decays at some very high scales. This is 10 to the third, 10 to the fourth, 10 to the fifth TeV. And the width of this just describes the uncertainty. So you can view the bottom of this as sort of an upper limit. Okay, the new physics has to appear above the bottom here somewhere. Now this, of course, this study, which was done by these gentlemen, you could say, okay, there are ways out of this. This is not, you know, this is not a case where we're saying definitively that there's nothing left. So the ways out are new particles have large masses greater than a TeV. They're up high, somewhere high here. They're at 10 TeV or 100 TeV. That new particles have degenerate masses. That works because the loops, you can have two particles in a loop with opposite phases, both new particles, and you wouldn't see it. The mixing angles in the new sector are small, and they're the same as the standard model. That's called minimum flavor violation, and that's the content of this theory. Okay. The other thing you can say is, well, this implies strong constraints on the new physics, but it's really telling me that these coupling coefficients are really on the order of 10 to the minus 7 or so. So I shouldn't really expect to see anything because the coupling to the new physics is really small from any beyond the standard model operators. which is possible, but unlikely. Now, having brought that up, there are still a few issues where people are beginning to see things. One is beta tau nu. This is a tree-level process, so it violates the paradigm of the loop-level searches for new physics. And if you take the values measured for sine 2 beta, okay, from the CKM fit I showed you before without the direct measurement, and you take the predicted branching ratio of beta tau nu, and you did this a few years ago, you would have seen a fairly reasonable discrepancy here of about 2.5 sigma. But there was a new Bell measurement, and this one new measurement is in complete agreement with the standard model prediction. So we can rule that out. I bring that up because there are other results here. I don't have time to go through this. I want to get to some other stuff. But beta tau D and D star tau nu has been looked at by Babar. This is a fairly difficult analysis. Like the beta tau nu before it, it's trying to detect a final state with a missing neutrino. They see something that's 3.4 sigma above the standard model. We're waiting for updated measurements from Bell to confirm or reject this. Now, the point here in showing you these single results is that a given theoretical model must explain all the data. So people like looking at one particular instance of something violating the standard model. And there are more I could show you. But a real model has to satisfy all the experimental constraints. Odysseus has to get the arrow through all 12 axe handles. So one measurement in principle can beat the theorists, but when we look at experimental data, we actually want to see a consistent pattern. We don't want somebody yelling at me and saying, look, I found one bin in this angular distribution that doesn't agree with the standard model, which happens. And I say, well, show me the other consequences of this. Okay, now that I dropped this, which I was told not to. Okay, so you can actually look for Majorana neutrinos in heavy flavor decays. Okay, there was a good discussion on that, so I don't have to explain it. Here's the double beta decay diagram, and here's a diagram from B minus decay, which mimics this, but the coupling here is to muons and charm quarks, so it's different. And this has been looked for by several experiments and not found, and this is sensitive to Majorana neutrinos at any mass level, because you're looking for a branching ratio that can't exist in the standard model. So this is kind of nice. Okay. There's another thing you can do is to look for fourth generation neutrinos that have different right-handed couplings, for example, where you have a BDU decay, it annihilates into a W, and then it goes into a mu and a neutrino, and the neutrino is Majorana, so it can go back to a mu and a W, and W can manifest itself as a pion or a D sub S or something. And there are many other ways of searching, and there are other limits that I don't have time to show you. If you want more details, look at this very nice paper. LHCb has searched as a function of neutrino mass and lifetime. So these are the results for different lifetimes of the neutrino. You should see a peak in the mass if there was really a neutrino here. Well, you don't see any peaks. So you get these upper limits, which can be translated via models to a limit on the coupling of a muon and a fourth generation neutrino. Okay. The dark sector. Could it be there are three classes of matter, standard model particles with charges, dark matter with dark charges, some matter having both, which we call mediators. Okay, there are searches for lots of dark things. I'll just talk a little bit about photons. The mediator can couple to B quarks, which is a nice result from Babar, where they look at 1s decays and two invisible particles and they don't see any. And there are other experiments. So here's a summary. This is the mixing described by the mediator here, and this is the mass of a dark photon. And you can see that experiments are beginning to fill this area, and this is a very interesting search region, but nothing so far has been found. And you can do it in lots of ways. So let me get to my conclusions. Although there's no compelling evidence yet for new physics, flavor physics is sensitive to potential effects at high mass scales. All new physics theories must satisfy stringent experimental constraints. Improving measurements such as Bs to mu mu, B to K mu mu, CP violation of phi s may show new physics effects and need to be aggressively pursued. There are other possibilities of interest. Understand meson substructure or the F0, 500, and 980 tetraquarks, What's the structure of the heavy charged upsilon states, the ZB, the charmonium states? Are there any heavy right-handed neutrinos? I think they're telling me I have to finish. We're looking forward to flavor physics discoveries from the LHC and its upgrades, BESS and Super B, and we're looking forward to defining the theory behind the next standard model. I don't have time to go through this message from a theorist. I guess I do for a second. This is from Nima. He says, cast a wide net. If you try to go to higher energies, flavor is very important. And there are no guarantees, but he says, in my view, flavor is getting to be a lot more important than it was because we haven't seen anything else at the LHC. So there are new experiments being planned. I don't have time to go through them. And these are very important, and they will have much higher sensitivities, order of magnitude higher sensitivities. And that's it.
Thanks, Sheldon, for a very comprehensive talk. Question?
The beta equation is at best ambiguous, and at worst it's incorrect. And the reason is you cannot take a fundamental matter particle and decay it into other fundamental matter particles. The new physics required to correct the problem is you have to add a Higgs force to each matter particle. And now the new equation reads as follows. The down part plus its Higgs force evaporates up to the super force. Now you have energy, which is easily subdivided into two parts. The first part condenses into the up quark matter particle and its Higgs force, and the second part into the W minus transient matter particle and its Higgs force. The W minus boson is really a W minus transient matter particle because within 10 to the minus 25th seconds, it evaporates back to the superforce. Now you have energy subdivides into two parts. One part condenses into the electron and its Higgs force, and the second part into the electron neutrino, electron neutrino, and its Higgs force. Do you agree that there's a fundamental problem with the definition of beta decay?
No, I don't understand it. Thank you for the comment.
Would you care to make a gentleman's bet on that?
Any other comments or questions? So let me remind you that we need to reset up the room. So we have to, let's thank all the speakers again, please.